Hello, YouTube Live. Again. Hey. It's loading my picture. There we go. Now I can see. So this is me talking to myself. I'm going to get attacked by the cat. Nobody's watching yet. So, if I open that one, switch to that one, I can I am back. Hello, hello. We have people. We have 7 people. Look at that. And a couple in chat. Excellent. Give it another couple of minutes to see if anyone else is going to join. And then you can see, hopefully, the plan. So we're going to go through this this specification, make some notes, and then hopefully do some questions. There we go. Good evening, good evening. Hello, 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 hello. Look at that, isn't that exciting? Oh, I've got a bit of a cold. However, we will persevere, and I'm going to eat some chocolate. I was going to try and find out how to mute my microphone. I just do that. Tom, mate. Yeah. We'll see how that goes. Loving the live streams. I'm glad. I am glad. I too am loving the live streams. Okay. It is past 9 o'clock. So if people are coming, they're here. Or they'll be here shortly. So, should we get started? Should we first of all have a think about current? So this is the specification, and we've got the whole. Can't wait for this. And we've got the whole specification for the topic 5, which is electricity, in the live stream. George, Rebecca, were you Hadoop or something the other day? Anyway, let's start with current. So current is a net flow of charged particles. Well, that's it really, a net flow of charged particles. Generally, we're talking about a wire. So in a wire, in a metallic conductor, such as this one, oh, sorry, George, I'll confuse you with someone else. We have a lattice, a 3-dimensional lattice of positive ions. So this repeating 3-dimensional structure of positive ions held together or chemically bonded by electrons. But in their chemical bonding, they have electrons which are not associated with any atom or any ion, any positive ion in particular. And generally they just bob about all over the place. They go everywhere. But if we apply a potential difference between one side and the other, then they tend to have, so some of them will still be going the other way, but they tend to have a net movement in one direction. So if our electrons have all got a net movement to the right, my current I is travelling to the left. So this is conventional current. And that tells me that this side is positive and this side is negative. Conventional current flows from positive to negative, which is counterintuitive because electrons flow from negative to positive. So negative things are repelled by negative things and attracted to positive things. 12 watching. I was hoping for 10. That is more than I could have ever hoped for. If we choose a point, and I could choose a different colour, but I haven't quite figured that out yet. So if I choose a point, say this point here, and I measure the amount of charge, or if we were really keen, we can measure the number of electrons passing that point per second, but we can find out the number of electrons, the charge in electrons. Well, the record was 7, George, so now 12 is huge. So if we find the number of electrons passing a point per second, multiply that by the charge on each electron, we get the charge flowing past a point per second, which is a definition of current, or at least a definition of current at this stage in our game. Hello, Jack's mum. It's very nice to see you. So we've got this thing that we call a potential difference. Now, when you get to A2 and you learn about fields, you'll understand that there's an electric field set up in the wire going this way. So that would be the direction that a positive charge would flow, so from the positive to the negative, which when we get to it next year, or for those people in the second year, we talk about a potential difference. There's a difference in potential V, and that's going to be the work done, or delta W, per unit charge Q, in order to move an electron from one place to another. So we're going to set up a potential difference from one side to the other, and that's going to cause our electrons to move. So they're going to move from a region for them of higher potential to a lower potential. Just like if I had an object in a gravitational field and I dropped it, it would move to a region of lower potential. So before we move on to resistance, if we just take a look at our units, so for current, we measure current, so I in amps, and 1 amp, let's undo that, so 1 amp is 1 Coulomb flowing past a point per second. One of the things that they like to ask you in exams is what's the base unit for a Coulomb. So if we rearrange our equation up here to find delta Q is I delta T, then we find that 1 Coulomb is 1 amp second. And that's one of those annoying units that is not very intuitive. So they like to ask you about it. They like to pop it in with one of the questions which got units ... and you get a mark for the units. Or they ask you in a multiple choice question, what are the SI units for charge? So that'll be amp seconds. Not in base units, but we need to know that potential. I'm not going to sing my special song, Jack. I'm too ill, I'm afraid. Hello to Beth, Jack's mum. It's very nice to see you. In terms of voltage, without singing a song, 1 volt is 1 joule for every coulomb of charge that passes through that potential difference. Now, potential differences, we're going to say, are usually from one side of a source of EMF to the other side of a source of EMF. So we pass current all the way around the circuit, or we can measure current. We can measure a potential difference across a component, so we can see how much energy per coulomb is is needed to move an electron from one side of the component to the other. Resistance depends on these properties here. We'll talk more about what resistance actually depends on later, but resistance is how difficult it is to make current flow, to make electrons move through a component. So we measure this in ohms, so resistance R in ohms, and ohms is Greek capital omega, and it's the potential difference per unit current. So how much push or how much energy do I need to provide per unit charge to create a current? So if I've got a higher potential difference, so we put this over here, I didn't want V, so for resistance is potential difference over current. If we increase the potential difference, we don't want to do that. What should we do? If we change our resistor out for a resistor with higher resistance, we have the same potential difference across it. If we've got the same potential difference across a higher resistance, our current goes down. Okay? If we wanted the same current, we would have to provide a higher potential difference. We're going to talk a bit more about resistance later when we get to resistivity, so we'll leave it there for the basics of electricity. If you've got any questions, do pop them in the live chat. I still need to figure out if I can mute sound. Microphone. Okay, I'm back. Hopefully that worked, and you didn't hear me blowing my nose. Fingers crossed. 14 people come to watch now. You should be able to scroll back if you want to catch up, or if you're feeling okay with it, we'll carry on. You can catch up later. The next thing we want to look at is current voltage characteristics. In this specification, what they tend to do is try to confuse you. So if we take our axes for our graphs as 4 quadrants, we've got positive and negative regions, they'll tend to put I on the y-axis and V on the x-axis. Although it says here questions can be set where either I or V is on the horizontal axis, so we could have situations where we've got V here and I here. Right, I can't do this without the song. George, you've never heard the song, unless you're using a pseudonym. Tom, how do you work out what current flows when you apply a voltage across something with zero resistance? You do ask the best questions. So you want to guess then if there's zero resistance you get an infinite current. But as I don't know if you can see my liked videos, we watched a video earlier from the Royal Institute, where they made a Mobius strip with a superconducting magnet on, and a superconductor on a strip of magnets. And you've probably seen the I don't know what it's called, levitating little car going around the track. No, we're not going to have the song. Sorry. Oh, George. Okay. I didn't know your middle name, but now I do. You have heard the song. You're in my tutor group. Right. Anyway, we have what it says in the Royal Institute video is that you still have a tiny resistance. So even superconductors have a tiny resistance. You won't get an infinite current, which would be awesome, but also pretty crazy. So let's go back to current voltage characteristic graphs. We'll start off with an ohmic conductor, because that's the easiest one to draw. So an ohmic conductor is a conductor, so any metallic conductor really, which follows Ohm's law. Harley Kelly is owed a shout out. He was the first person in his class to reach iron 56 in the fusion game. Now that is something to be proud of. I think Harley should be proud, and well done. Well done. Good to see you. Okay, that's lovely. Shout out complete. There are other people who require a shout out, including I think Mr. Matthew Burford, but I don't think he's here. No problem, Harley. You be proud. Let's go back to ohmic conductors. So things that obey Ohm's law we call ohmic conductors. Hi Will. They include wires. They try to include fixed resistors, but in real circumstances, things don't obey Ohm's law. When they get hot, their resistance increases. We'll have a look at that in a second. But if we keep constant physical conditions, so if you're talking about things obeying Ohm's law and you're asked about it in an exam, then you're talking about things under constant physical conditions, which means controlled temperature, really. At this stage. So for an ohmic conductor, we have constant resistance, which means we've got a constant ratio of current to voltage, and actually both our graphs look exactly the same. Yep. So in this graph here, our gradient, which is constant, so we've got a fixed resistance, we've got our gradient is a change in current over a change in potential difference. So our gradient is actually 1 over the resistance. In this graph here, this is the one that I like to use, this is the one I like to draw, because the gradient here is simply the resistance. That makes life easier. So these are both for ohmic conductors. Things with fixed resistance, things with a resistance which doesn't change under constant physical conditions. Okay. Our semiconductor diode is quite similar. I think what I'll do is I'll stick with the easy one. So we put a V on there. Oh no, I don't want to do that. No, I don't want to do that. We'll go for the hard one, just to make things harder for everybody. So in this case, a diode, the idea behind a diode is it only allows current to flow in one direction, just like the band. Okay, so over here, in the reverse direction, we have zero current. Yeah, maybe if I go here, draw this in red, because otherwise you're not going to be able to see it. So here we have zero current, and actually up to a value of 0.6 volts, and we've still got zero current. Past the threshold voltage of 0.6 volts, when we provide enough energy to elevate the energy level of some of the electrons, so we get electrons in a conduction band, then we get a current to flow. And at this point, it behaves, or our silicon diode behaves like a fixed resistor when we've got constant physical conditions. So this one here is a semiconductor, probably, lost the edge, diode. finally, for this one, we want the filament lamp. This is our most complicated of our three. It's going to involve us going back to our diagram at the top for resistance. So in a real situation, in our metallic conductor, it looks like this. When we increase the current, these electrons are passing through the wire, and there are collisions. There are collisions between the electrons, there are collisions between the electrons and the positive ions in the lattice, and it increases the temperature by increasing the amount that these ions in the lattice vibrate in all directions in 3 dimensions. By increasing the temperature and increasing the vibration, it makes it more difficult for the electrons to flow. So if it's more difficult for the electrons to flow, we require a higher voltage to get the same current to flow. Okay, so let's go back down to this one. So if we require a higher voltage to get the same current to flow, we get less and less of an increase in current as we increase the voltage. So if we start down here, maybe in both directions, we get something similar to a fixed resistor here, but as we increase the potential difference, as we increase the current, the conductor gets hot. So the gradient here decreases as the temperature rises and the resistance increases, and all we can do here is we can find the resistance at individual positions. Okay, so if I want to do that, I would take a value for the current and the value for the resistance, and then well, we'd probably just do I as V over I if we weren't taking any gradients. Okay, so those are the 3 situations. This one here is a filament lamp that you need to remember and explain. I should add in here that here this threshold voltage is 0.6 volts for most diodes. These are the 3 situations you need to explain. So ohmic conductors are fixed resistors, semiconductors which only allow current to flow in one direction but otherwise behave as a fixed resistor, and then the filament lamp, which the resistance increases with increased current, increased current, so it requires a larger voltage to get the same increase in current. Unless specifically stated in questions, ammeters and voltmeters should be treated as ideal, so respectively having 0 and infinite resistance. So if I had a circuit, which I'm going to run out of space to draw, but I'll do it, I've got space up here, let's do it over here. So if I've got a circuit which has a cell and a resistor, nice and simple. If I want to measure the current, what I'm trying to find is the charge flowing past a point per second. So if you imagine I've got a counter, and that counter is counting the electrons, it needs to be in the loop. So my ammeter goes in the circuit, but it's measuring the current. We don't want it to affect the current. So if this is ideal, and it's in the circuit, the resistance is 0 ohms, if it's ideal. If we have a voltmeter, so we're measuring the potential difference here across one side to the other side of this resistor, V. If this one is ideal, then the resistance equals infinity. Okay, so what we don't want is any current flowing around this part of the circuit. If we did have current flowing around this part of the circuit, then we'd be altering the system that we're measuring, which in real terms we always do when we measure something, but we don't want that to happen. Do we need to know the ideal ammeter and voltmeter for the exams? Yes, Jack. Everything in these typed parts here, yeah, you need to know. This is a specification from AQA. The link should be in the description, and you do need to know that. If the question states that they are not ideal, they might treat this voltmeter, for example, as a resistor, or you might treat this ammeter as a resistor, and that would change the way you do your calculations. Okay, and we've talked about this bottom one here, where we can either have V or I on the X and Y axis, and we can switch those around, but making sure we remember they're different. The gradient means something different in both cases. That's a reciprocal of the other. Okie doke. Resistivity. If you imagine a wire, you don't have to imagine a wire, I can draw a wire, possibly. It looks like this. And if we use an analogy of this being a pipe, like a pipe of water, if I make the wire of a greater cross section, then I'm going to get more water flowing through the pipe. So I like to think of this equation slightly differently. If we imagine we change the length and nothing else, it's going to be more difficult due to friction to pass water through that pipe. So bigger diameter, bigger cross-sectional area, easier to make current flow. Longer wire, harder to make current flow. Okay? Which tells me that my resistance, so as length goes up, resistance goes up. So resistance is proportional to length. The other one tells me that resistance is proportional to, well, as cross-sectional area increases, resistance decreases. So they're inversely proportional. Then we need a constant of proportionality, and in this case we're going to call that resistivity. So my resistance equals the resistivity multiplied by the length divided by the cross-sectional area. So if you could think about this resistivity as a property of metals, or a property of any conductor. If you think about it in terms of water pipes, maybe you've got more stones or less stones in your water pipe, so it makes it easier or harder by definition for a current to flow through. If we take a look up here and we look at this, and if we want to find the units, we've got ohms multiplied by meters squared for cross-sectional area divided by meters. We're going to cancel there, and we're going to cancel there. So the units for resistivity are ohm meters, and that's another one of those units, a bit like the base units for the Coulomb, which they might ask you to give in an answer, because they're a bit awkward. They're not normal. They're not something that you've learnt at GCSE. They're new, so they're something that they'd like to test you on. If you had a conic wire, would you have DA? Would it have to separate? Not quite sure what you mean by separate. But if we had an increasing cross-sectional area, then you would have a gradient of resistance. So I think, if I've read your question right, George, then you would have DA. So you would have a changing area, so you'd have a changing resistance. As we talk about resistivity, cross-sectional area for a wire is pi r squared, if you know the radius, or we can replace the radius with the diameter, is pi d squared over 4. So this is A for a wire. Do I need to know about Ntc Thermistors? Oh, that's a good question, Tyler. I don't know, but yes, you should know about them from GCSE already, so I'm going to go with yes. And we can talk about them when we get to potential dividers, and you do need to know about potential dividers, so you can do about sensing circuits as well. So yes, we need to know about Ntc Thermistors. But Ntc Thermistors are just the thermistors that you've done before. It just means the negative temperature coefficient means that as the temperature goes up, the resistance goes down. Yep. For another case, sometimes I like to ask you about a strip. And a strip is going to have a rectangular cross section. Okay, so the area for a strip is a width times the, well, let's do the width times the height. Yep, if we label these up as W and H. Everybody knows how to calculate the area of a rectangle, but when they ask you about a strip of wire, that can get a little bit more confusing because it's not normal. Anything that's not normal, anything that can confuse, you like to throw in. So it's best to know all these tips and tricks. Okay. Description of the qualitative effect of temperature on the resistance of metal conductors and thermistors. So what we've said already, let's go over here. So a metallic conductor in real circumstances, if we have a graph of resistance in ohms against temperature, let's go with Kelvin. For a metallic conductor, as temperature increases, resistance increases. So, if we could cool things down to absolute zero, there'd be no resistance. We'll talk about another case in a minute, but I've missed. Hang on. Boom. So we tend to get an increase in resistance with temperature for a metallic conductor. Whether it is a straight line isn't something that we need to worry about, because we only need a qualitative description of the effect of temperature on resistance. So if you say as a metal conductor increases in temperature, the resistance increases, that will be fine. For a thermistor, it's slightly more complicated. We don't talk about the nature of this curve, but what we do say is that the resistance in ohms for a negative temperature, that's awful, in Kelvin, what we do say is that the resistance decrease is as temperature increases. So we've got a metallic conductor and a thermistor, how they change with temperature. We've got one more. We'll come back to thermistors as temperature sensors later, because it makes more sense to do that when we talk about potential dividers, because they're really useful there, and they like to include thermistors in potential dividers so they can vary the temperature, indirectly vary the resistance. In the question, it's indirect, just to make sure that you know what you're talking about. For a superconductor, we have a different graph. Tom touched on it earlier, but for a superconductor, at or below a certain temperature, and that at or below is quite important, at or below a certain temperature in Kelvin, we have, so this is resistance in ohms again, this is temperature in Kelvin, at or below a certain temperature, and this is what we're going to call our critical temperature, which is up here. Superconductors are super cool. However, the race is on to find a superconductor which is a superconductor when it's not super cool. So when it's something like at room temperature. That would be the most useful thing, because superconductors are really, really useful, and we would help the world a huge amount by reducing losses in power as we transfer electricity, which would be brilliant. What's really important about critical temperature is you say at and below. Yeah. Yes, Jack. Superheated superconductor would make our lives easier. Yes. I'm not sure why it would need to be superheated. Superheated relative to normal superconductors. So in the Royal Institute video that I was talking about earlier, then if someone's got a link to that to put it in the chat, that would be really useful. They say they've got a high temperature superconducting material, which is fab, and then they tell you the high temperature is somewhere close to the boiling point of liquid nitrogen, which is something like minus 183 degrees, which is still pretty cold. But superconductors are really useful. We can use superconductors to produce strong magnetic fields. Why would you want a strong magnetic field? I hear you cry. Usually for MRI scanners. So if you're asked for an application of superconductors, it's to make superconducting magnets. That gives us really strong magnets. We can get super high currents, and super high currents induce super strong magnetic fields from a superconducting magnet, which would give us a huge magnetic field, which means that we can scan for tiny electrical currents and spinning protons in the brain. We can also make frogs float. Thank you, Tom. Possibly not the most useful applications. If you put that in your paper, I'm not 100% sure that they'll give you the marks for that one. Quantum levitation is your favourite thing. Excellent, Jack. Good to know. The second use is to reduce energy loss in the transmission of electric power. So superconducting power lines. So superconducting power lines would be brilliant because we reduce energy loss. We lose a lot of energy to heating, so we've got birds sat on the wires heating their feet up, and they're using our electricity. So power lines are not 100% efficient. So we have lots of losses which we don't want. So as soon as... Excellent, thanks George. You can't link in the chat, but if you Google RI or Royal Institute Superconductors, it's the first thing that comes up. So as soon as we've got fusion and superconducting power lines at room temperatures, or slightly less if they're outdoors in England, then the world would be an easier, cheaper place to live. Okie doke. Circuits. There are a bunch of circuit symbols that you could learn. Ones that really matter are, let's go up here a little bit, cells of some description, or more than one cell, resistors, filament bulbs, we've got a thermistor, whoop, looks like that, we've got a variable resistor. You can place diodes wherever you like, Jack, as long as you get them in the right orientation, otherwise you'll get no current. Those are really useful. Diodes, because we talked about those earlier, have a symbol that looks like that. So this is when you're drawing a circuit, but actually it's more important for you all to know these when you're interpreting circuit diagrams in questions. So let's talk about a very simple circuit. A very simple circuit, which is a cell in series with a resistor. So in series we have one loop. In series we've got one loop. In this case we've got a cell in our loop and a resistor in our loop. I think it's probably best if we talk about current in series circuits first. So in this circuit, our long side of our cell is positive and our short side is negative. So our current flows, our conventional current flows from positive to negative. Guessing that the current goes in the direction of the arrow. Yeah, that's absolutely right. So for our diode here, current goes in that direction. So think of it like a play symbol. Play means it's going to go in that direction. So in this circuit here, our current everywhere is the same. So in a series loop, our current is the same everywhere. No problem. In our series loop, our potential difference is shared between our resistors. So in this case, if we had a cell of say 3 volts, then we get a potential difference across our resistor here of 3 volts. If I put in a second identical resistor, like so, okay, if we put in a second identical resistor, then this one would get 1.5 volts, and this one would get 1.5 volts. Brett, in answer to your question, why do they flow in different directions? In this loop, if I follow it around, my current is going the same direction all the time. Yep. So my current is always flowing positive towards negative. Or my conventional current is flowing positive towards negative. Now, if I had a different combination of resistors in a series loop, so say I had 2 resistors again, so these two both have the same resistance, R and R, but this time this one has got 1 ohm of resistance and this has 2 ohms. So in this case, in series circuits, my potential difference is going to divide between the 2 resistors in proportion with the resistances. Okay, so this one will get 1 volt, that's a smaller resistor, and this one will get 2 volts. The way I think about it is I have to get the same current to flow through both of these resistors. Yep, because it's the same on both sides in a series loop. So if I'm going through those resistors with the same current, it's going to take me twice as much energy per unit charge to get through a resistor, which is twice as big. Apologies if the kettle's a bit loud. What should we do next? If I put 2, so we've got resistors in series. If I put 2 cells in series with one another, we can put a wire between, or we can not. If we put 2 cells in series, then the potential difference adds. So if I've got 2 3-volt cells, then here I'd get a potential difference of 6 volts. So in any case, the sum of my potential differences in is going to be equal to the sum of my potential differences out, and that's going to be Kirchhoff's loop rule. So in any closed loop, the sum of the potential differences equals 0. So we've got our potential differences in from our cells, or our EMF. It's not for me, Carl, I don't drink tea. So our potential differences in are equal to our potential differences out. So in this case up here, when we had 3 volts in, we had 3 volts out, so we've got our in minus our out. The sum of the potential differences equals 0. So that makes us happy for series circuits. I know, no tea, no coffee, no hot chocolate, no hot drinks, full stop. Where should we go next? Ooh, I think we should stick with this one. So this, the example we just talked about, is an example of conservation of energy. So if we're transferring energy into a circuit, we're going to call that an EMF, and we'll talk about that a little bit later on. Then we have to be transferring energy out of the circuit. So in the case of a resistor, that energy is lost through heating of the resistor, and we can look at our power equations in a second. Although this looks quite small, there's quite a lot in this, and I'm going to run out of space. So let's think of Kirchhoff's loop rule as conservation of energy. If we talk about conservation of charge, black coffee, I don't think, oh, he's got coffee, that is true, although you're quite far away, I hope. If we think about charge, the sum of the currents entering a junction, so this is for a loop, this is for a junction, this is Kirchhoff's junction rule. So if I've got a junction here with some wires coming into it, I've got one going in, one going out, and the other going out. If I call this I1, if I call this I2, call this I3, then I1 equals I2 plus I3. Oh, I'd put it another way, I1 minus I2 minus I3 equals 0. So the sum of all the currents into a junction and exiting a junction equals 0. So that's Kirchhoff's junction rule, that's Kirchhoff's loop rule. This means that charge is conserved, so whatever charge is going into vertices or vertex is going out. Let's take on parallel circuits. So in a parallel circuit, we tend to draw it with branches which are parallel to one another. So we know now that if I've got a current here, then my current is going to, so call that I1, this one will be I2, this one will be I3. Not sure what you mean there, George. If I've got I1 meeting this junction here, then it's going to split into I2 and I3. And what's going to happen is it's going to split inversely proportionally to the resistances. So if this is a higher resistance, it's harder for current to flow, so we get less current. If this is then the lower resistance, it's easier for current to flow, then I3 would be bigger than I2. For each of the branches in a parallel circuit, the voltage is the same. So if I've got 3 volts up here, I've got 3 volts down here, and 3 volts down here. Now you might be thinking, but wait, now they've all got the same voltage, we've created extra energy. That's not the case. As we'll look at when we talk about power in a minute, if power is current times voltage, or current times potential difference, then up here we've got a bigger current times the same potential difference, and each of these has a smaller current multiplied by potential difference. If we put cells in parallel, then the same rules apply. So what we get is, so when we had cells in series, the potential difference is added. In this case, from what we know already, if we have 3 volts here and 3 volts here, on parallel branches, we get the same potential difference here. But to get the same current to flow, we have less current from each cell. So if I want a certain current and I put cells in parallel, each cell has less current flowing through it, and they add together to make the current that we want through our component. So if we think about current as the flow of charge per unit time, then we have less charge flowing through each battery per unit time, which means our batteries go flat in a longer time. So this gives us longevity in our batteries when we put them in parallel. If we put them in series, we can get a higher potential difference and more current flowing through each cell. So currents, voltage, resistance, series power circuits. Right. So the next thing we need to look at is resistances. So in series circuits, if I've got some resistors like this, we always have to have the same current flowing through each of them. So going through here, the current is the same, but the voltage is different, and we know that the voltages add up. So if this was let's call this V1, V2, V3, and then if we look across the whole thing, let's call it not V4. Let's call it VT. So our total voltage, or our total potential difference. You're right, Jack, the current here should be in the other direction. I knew I was going to do it. So it's going up. 100% Jack, gold star. Now, if we've got our total resistance across here, then from what we said about the way voltage or potential difference splits across resistors in series, then we get V1 plus V2 plus V3 is our total potential difference. Now we know that potential difference is IR, so if we get IRT, which is our total resistance for this network of resistors, then that's the same as IR1 plus IR2 plus IR3, because we know that the current in each of these places has to be the same. So I can divide through on both sides of this equation to find, I'll get rid of that one as well, whoop, little tiny one, our total resistance is equal to the sum of the resistors individual values in series. Oh, well, you can watch later. Broker's internet. In parallel, so this is series. In parallel, we know if we've got a network of resistors, let's do 3 again. This can continue for as long as we want, by the way. So this can go plus dot 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 Rn. So however many resistors you've got adds up. Just add them all up in series. In parallel, we know that this current here, I total, is the sum of these 3 currents here. I'll call them I1, I2, and I3. So we've got my IT equals I1 plus I2 plus I3. We know that I is V over R. We know that for each of our parallel branches, the potential difference is the same. You can probably see where this is going already. And in this case, we can cancel all of our V's to give us the reciprocal of the total resistance is equal to the reciprocal of the first resistor plus reciprocal of the second plus the reciprocal of the third plus dot 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 the reciprocal of however many you've got. One big tip: once you've figured out your combination of resistors, you've added up 1 over R1 plus 1 over R2 plus 1 over R3, please don't forget to take the reciprocal of your answer, because otherwise you will get the answer wrong. Fab. So that's resistors in series, resistors in parallel, how we add up resistances in series and parallel, and actually how we got to it. So this is because we know this is because of our loop rule, and this is because of our junction rule for direct current circuits. We only do direct current circuits in the first year. They've moved AC alternating current to the second year. Power. There's not a huge amount to say about power, except I looked at it earlier, and we've got something like 8 different equations for power across the whole course, which is a bit of a nightmare. So power in an electric circuit is the current multiplied by the voltage, or the potential difference. We can sub in if we know that I equals V over R. We can sub in for I, and we end up with V squared over R. Or if we know that V equals IR, then we can sub in for V into here, and we get the power is I squared R. Generally, we know that power is energy transferred per unit time. So energy equals power times time. So if you times any of these by time, you'll get the energy transferred. So here's an example that energy transferred is current times voltage multiplied by time. Before we get on to potential dividers, I think we've done all of that. I'm going to take 2 minutes to grab a glass of water, and I'll be back. So let's see if I can do this again. I can give you my be right back sign. There you go, and I'll put myself on mute and I'll be back. I am back, and I have chocolate. Just for me, sorry, not for everybody. Okie doke. We'll continue with potential dividers. Down to 7 watching now. Our peak of 15 has dropped away. So potential dividers literally divide potential. Our simplest potential divider is a network of resistors like this. So what I can do is I can put a component across either of these two resistors. Sharing is caring, but I can try and put it in the camera, but it just won't work. I do apologise, Tom. It's very nice chocolate, although it is white chocolate from Aldi's Everyday Essentials range. Remarkably good. For 30p. So my potential divider is literally dividing potential. We know that between these two resistors we are sharing our potential difference that came from our source. And we can put something in parallel across these two resistors, which gives us some kind of output voltage. White chocolate's the best kind of chocolate choice. What are you on? It's my favourite at the very least. I'm gonna cheat and put a V in up here. I'm gonna call this resistor R2 and this resistor R1. Now we know that my voltage is shared between these resistors in the ratio whatever my resistance is. It doesn't have to be R2 or R1 over R1 plus R2. So that will give me the fraction of the potential difference in the circuit that I'm getting across one of my resistors. So if I multiply my input resistance by that fraction, I get on T, no I don't like tea, I wish I had some Coke, but I'm banned from drinking Coke, it's addictive. I get my V out. So if I got V in times by the fraction of the total resistance in my circuit for each resistor, then I get my V out. If I put that V out in parallel with the resistor that I had. Okay, we don't need to worry about the use of potentiometer as a measuring instrument, so I just crossed that one out. There are other ways we can draw the potential divider. One way, which is quite common, if we put our V in here, and we have this one like this, is to have a really long resistor like this. It is, Jack. Yeah, you're absolutely right. So if I have a really long resistor, and actually in the IB formula book they give you this symbol here, so just this part, as a potentiometer, sometimes called a rheostat. I'm sure there's a difference, but I couldn't tell you what it is. So here is our V out. So we can move this up and down to change how much of this resistor is across my V out. So here it's halfway along, so we're splitting evenly our V in 50-50. So what we're talking about is ratios. So if I talk about the length of my resistor, I said it's about halfway along, so it's about 50-50. That's my total length L. Let's call this part L1, this part L2. Because we're talking about ratios, we don't need to worry about our units. So we can say that the ratio that my my potential difference is going to split in is L2 over L1 plus L2. And if I times V in, I'll put a dot there for you, Jack, so you know that it's times. If I times V in by that ratio, I also get V out. So that's two examples of how you might see a potential divider circuit. This is a simple example. It'd be really kind of them to give you that. This is a slightly more complicated example. You can talk about the resistance of this part, and you can talk about the resistance of this part, or you can just talk about the lengths of the two parts. And you can slide this normally up and down. In a volume control, for example, you might have that in a ring and spin it. However you vary the split in the potential difference, it is fine. What's useful about potential dividers is if I move my slider down to here, V out equals 0. If I move my slider up to here, V out equals V in. Okay, so I've got my whole potential difference across there. This is different from using a variable resistor. So your first thought is, right, I'll use a variable resistor, and I'll be able to change from maximum to minimum. But actually, if you've got a variable resistor, you cannot get your minimum out. And we could talk it through, but we won't, because it's 10 o'clock. We've got 2 more bits to do, and then some questions. I'm hoping to finish at about 10:30, because it'll be my bedtime. And Nick did tell me off the other day when I started streaming at 11:30, told me that everybody should be in bed. So, we need to talk about the use of variable resistors, thermistors, and LDRs, or light-dependent resistors, in a potential divider. So, let's have a situation where we've got our simplest form of potential divider. Our V out comes across here, and this time is a thermistor. Okay, if I increase the resistance of my thermistor, and if you remember, to increase the resistance of my thermistor, I cool it down. If I increase the resistance of this, then the share of the potential difference that this gets in relation to this increases, which means that V out increases. Okay? If I decrease the resistance of this for a thermostat, that would be by heating it, then V out would decrease, because the resistance would decrease here, which means that this one would be bigger compared to this one, which means that this would get a larger share of the potential difference. We get exactly the same scenario if we have an LDR. We can literally replace that with an LDR. I don't think we've drawn an LDR. So it's a resistor which depends on light, which is incident on it. A light dependent resistor, which is up here. Yeah. So resistors and thermistors is the same thing, but for an LDR, as light intensity increases, resistance decreases. So we can replace our thermistor with our LDR when we're talking about temperature and light intensity. We can switch them out. So I wonder if I can do this. If I move V out and get rid of that one, if I move V out across this one, now we've got the opposite situation. So if I increase the resistance of my thermistor by cooling it, then this one gets a larger share of the voltage, and my V out across the other resistor drops. If I decrease my resistance of this one, PVD, potential divider. If I decrease resistance to this one by heating it, my V out across this one goes up, so this one gets a larger share. Tyler, can you clarify what a PVD is? Any inefficiencies when we've got our maximum output, if this is what you're talking about, would be in our wires, and we would tend to say that our wires are ideal, they've got zero resistance. Potential voltage divider. Just stick with potential divider, because potential and voltage are kind of the same thing. The dog wants to be in the stream now. Similar situation if we replace our thermistor or our LDR with a variable resistor, except that reduces your workload because you can see directly whether the resistance goes up or down. For a thermistor and an LDR, you need to know that as the temperature increases, the resistance decreases, or as the light intensity increases, the resistance decreases. Okay. Potential dividers. People find potential dividers quite difficult, but as long as you're aware of your circuit rules, you should be fine. Okay, so this is our last section in terms of going through the spec before we start to do a couple of questions. We're talking about EMF and internal resistance. I'm going to scrub this out. I don't like calling it electromotive force. It is not a force. No, no, no. EMF? Yes. Bad name. Really bad name. So we'll call it EMF. We'll get rid of that force altogether because people get confused. You think you call something a force, it's a force. But in this case, no, it is not. So when we talk about EMF, we've got an equation that looks like that, and it looks quite a lot like our voltage or our potential difference equation. So it's energy transferred per unit charge. So that's energy transferred into the circuit by a power source. Okay, so it's energy supplied per unit charge in moving a charge around the circuit. I'm not going to write that all down because it's a right pain, but it's energy supplied per unit charge in moving that charge around a circuit. Now, if we talk about a perfect source, which we're going to draw just as our cell, then that would have an EMF equivalent to the voltage we measure across it. However, we often don't have a perfect source. So what we draw is inside our source, so this could be a cell, it's usually a cell, because cells do have internal resistance. Not often very high, but they do have internal resistance. We'll call that internal resistance R. So this is a model. So that's a perfect source of EMF, and this is an internal resistance. So from what we've learnt already about our splitting or our potential difference required across a component, across here we have some potential difference, and we're going to call that small v. Excuse me, we're going to call that small v, and that's going to be our lost volts. So these are lost before we get anything out of the cell. If we want to measure the EMF of a cell, we make it so that we've got no current flowing through the cell. So you put a voltmeter across the cell with nothing else in the circuit, and you can measure the EMF. As soon as you've got current flowing through the circuit, there's a current flowing through this resistor, and we've got lost volts equal to the current multiplied by the resistance of the internal resistor, which we're calling small r. So once we've got our EMF and our lost volts, then across the whole system we have big V. So big V is our terminal potential difference. So our terminal potential difference is the potential difference at the terminals of the cell, the positive and the negative, when we've got a load on the cell. So when we've got something else in the circuit, when there's current flowing around. In order to find the EMF, we have to take the terminal potential difference and add it to the lost volts. Okay? Now, for a single loop, we know that the current flowing through both is going to be the same. So if we factorize out our current, we arrive at this equation up here. Okay, so these are V equals IR from our Ohmic Conductors Ohm's law calculation earlier, or our definition for resistance. You will be expected to understand and perform calculations for circuits in which the internal resistance of the supply is not negligible. So if it's not negligible, you replace your cell with a perfect source of EMF and a small internal resistor. Confused about what each thing actually represents and means. Each thing. So our dotty box is our cell, which in normal language is a battery, but a single battery, as we call them, is a cell. In a battery of cells, there's more than one cell. So this dotty line around here is a cell. Okay, inside that cell, we're modelling a perfect source of EMF and a resistor, and this is the resistance which is inside the cell. So if you were to open up a battery, which I do not recommend you do, it smells and it's bad and it's all sticky and you don't like it. If you open up that cell, then you'll find there's an electrolyte in there and it does not have zero resistance. Okay? So we have an internal resistance inside the cell. It's not easy, or it's not infinitely easy to make current pass through the cell. Unlikely to blow up, but just don't open batteries. Don't open batteries. So once we've got our perfect source of EMF, and we've got some volts lost across here, if we draw this in a full circuit, come over here, look. So if I draw this in a full circuit, a very simple circuit. No, don't blowtorch batteries, George. Don't do that. It tends to be that this is called big R, and that's the resistance of all the other stuff. This is the internal resistance of our cell, and all this we don't see. This is inside our cell. We don't see this. This is a model of the inside of a cell, a perfect source of EMF, and an internal resistance. If we measure the potential difference across the cell whilst current is flowing, and I'll get my current arrows the right way around this time, so there's a load across the cell, then this will be our terminal potential difference. Bad George indeed. Right, are there any questions with where we're up to, or shall we start doing some problems? I enjoy the fact that I've got a crown. Okay, I'm back. I've eaten chocolate. I'm fine. If the terminal potential difference changed, would the internal resistance change? The internal resistance wouldn't change, but if you increased the load on the cell, if you drew a larger current, then the lost volts would increase. So, for example, if I put the example they normally give is of a car battery. So if you put your headlights on, you have a low current. This isn't the middle of the night. I started at 9 o'clock. Anyway, if I have a car battery with some headlights, then the current is quite low. And then if I turn the starter motor on, then I draw a huge current. So that huge current increases the lost volts across the cell, and then your headlights go dim, which is lovely. Well, probably not what you want. Okay. Please feel free to ask any more questions that you have, whilst I grab some questions for you. Why do I do these so late at night? It's because I have children. I have to put the children to bed. I have to do all that kind of fun parent stuff before I then get to come and hang out with you guys and do physics. I think that's the right answer. Right. We've got a few minutes. Have a go at that one. A, B, C, or D. So what we're talking about is the relationship between resistance, resistivity, length, and area. And then for our area, so we've got a cylindrical conductor. For our area, our cross-sectional area is pi d squared over 4. Have a go. See what you can get. Please stop attacking me for doing live streams for you all. I've provided hints and everything. A, B, C, or D. It says 7 people are watching, but only 4 people are in chat, so it's up to you, George, Harley, Jack and Tom, who is going to be the winner. A, B, C or D. Thanks again to AQA for providing us with questions for free on their website. Jack would say C. Why would you say C, Jack? George would say B. Kyle is here and participating. How long have you been lurking there, Kyle? B, B, oh, all those B's. B is the correct answer. So if we replace A, so R is rho L over pi d squared over 4, and we say that this one, this one, this one, and this one are all constant, then we know that R is proportional to 1 over d squared. Oh dear, I did increase the resolution, Tom, because in the last one I don't think people could read the question. Is anyone else having the same problem as Tom? Obviously not, because you will give me answers. Long enough to hear about my disappointing lack of hot beverages. Okay, you do have to square that diameter. Be careful what I say. This is a kids show. So my new resistance, which I'm going to call R prime, is proportional to 1 over d over 2 all squared. So keep that as proportional to 1 over 4 d squared. So I've got a fraction on the bottom of a fraction. So R prime is proportional to 1 over 4. No, that's wrong. 4 times 1 over d squared. And if we hark back up to here, my original R was 1 over d squared. So my new R is proportional to 4 times my original R. I just don't have paper handy. Well, Jack, run! You've got a few minutes. I've run out of space on my thing, so I'm actually going to have to delete this one before I get the next one. So let me grab a doozy. That question's a bit rubbish. I quite like this one. It's a bit tricky. Oh, gotta love Jack. Let's go in and get paper. It's gonna need paper for this one. So, 3 identical cells, each of internal resistance R. 8 o'clock. 3 identical cells, each of internal resistance R, are connected in series with an external resistor of resistance R. So my internal resistance R is the same as my external resistance R, but I've got 3 lots of the internal resistance. The current in the external resistor is I. If one of the cells is reversed in the circuit, what's the new current in the external resistor? I might just draw this one out for you. So the way I draw it, I'd have 1, 2, 3 cells in series. I'm going to move their resistances out like this. And each of these has resistance R. All 4 of those. So that's my first situation. Didn't want to do that. Tyler's going to go with A. In my second situation, I reverse one of my cells. The internal resistance is still there, but one of my cells is reversed. So if this is initially V, 2 of these cancel each other out, so I end up with a third of my original potential difference. So my first instance, because we know that resistors add in series, my I is V over 4R. We could even convert that into, I believe, let's get rid of that, grab our colour again, over RT, because our resistance isn't going to change. Then our new current is V over 3 all over the same RT. Yep. So if I change this about a bit, I get V over RT multiplied by a third. But V over RT was my original I, so it's my original I over 3. I'm getting bugged by the dog to talk to the dog. You can now hear. So what I'll do, I think we've still got people watching, is I will get rid of that one for you. Give you a new one. Find a good one. Let's have a bit of a tricky potential divider one. Not too tricky. But still it's potential dividers and everybody hates them. I'm going to put the dog in the other room. Poor thing. Not that there's anything wrong. I promise. Sure we can pretend, Carl. Sure we can pretend. You absolutely got it right. And if you didn't, you can rewind and go and have another look. Right, I'm going to mute my microphone while the dog's whinging. Have a go at that one. I want to see a full complement of answers in the chat when I get back. I'm back. Ash is back. Don't worry. I haven't got a full complement of answers. Will, you're back. Your internet is fixed. That's fantastic news. Fantastic news indeed. I have dealt with my dog. She's in her bed. And I'll go and play with her as soon as we're finished. Jack wants to say D as well, but he's not really sure at this point. So why don't we this is annoying. Back in black? Oh, I don't know the words enough. This is a bit annoying because what they've done, I wonder if I can draw over this. Let's scrub that one out and that one out and draw them back in the other way round. Because as soon as we draw them back in the other way round, it looks like the potential dividers we were looking at earlier. Yay! I'm pretty sure the current will not stay the same as this junction. So this junction here, the resistance of my ideal voltmeter is infinite. Okay? So all of the current is going straight on. So I here equals 0. Harley says B, Tyler says D, Jack says D, George is feeling B. So the circuit shown, the diagram is negligible internal resistance in the cell. What happens to the reading of both meters when the resistance of R is decreased? So if R goes down, V stays the same. V equals IR. If V stays the same and R goes down, I has to go up. Okay, so I must go up. So either that one or that one. If I decrease R, when we were talking about potential dividers a minute ago, then we decrease the share of the potential difference that this one gets relative to this one. Okay, so this one becomes smaller compared to this one, whether it's bigger or smaller, it doesn't matter, but compared to this one it gets smaller than my resistance, my potential difference across my resistor decreases. So B is the correct answer. Yay! Right. We can probably fit in one more. I'll leave that one there while I find a nice one. Oh, nice. It's not nice. This is not a nice one, but it's tricky. So the examples that I'm giving you now are really quite tricky ones. I'm avoiding all the ones that ask for recall, because that's boring. You can just look at the answer and find out what that is. Right, grab that one, back into there, pop it in there. Well, I can see your workings from here, George. Oh no, wait, you can see my workings. Right, it's telling this circuit has an EMF of 2 volts. Yeah, Jack, everybody's going to struggle with potential dividers EMF, so we need to do extra practice, which is why you're here, which is excellent. So you're now going to struggle less than everybody else, because you've had some practice. So we had some practice with a potential divider. So we talked about the relationships in a potential divider circuit. Now we're going to talk about EMF. Okay? It says that when the variable resistor in a circuit has a resistance of 4 ohms, so if this is 4 ohms, then the potential difference across here is 1 volt. That's the terminal potential difference. Okay, so this cell is not ideal. We know that because EMF is 2 volts and the terminal potential is 1 volt. So if we know that our EMF equals our terminal potential plus our lost volts, my lost volts is 2 minus 1. So V equals 1 volt. I'm going to give people a minute and have some chocolate. Yep. So although these are multiple choice, it doesn't mean there's just one step. Got an A from Tyler. A reticent A, or is that too easy? That's probably too easy, I'd suggest. So the inside of my cell looks like this. This is my small r. So my small r, or well, what I need to do first is figure out the current. So I've got a terminal potential difference of 1 volt. It means I've got 1 volt across this cell. So I can move these anywhere I want along these wires. They've got no resistance. So I equals V over R. equals 1 over 4. So that's my current. So 0.25 amps is my current. But I also know I've got 1 volt across here. So without doing that, really, I know that the resistance in this one is 4 ohms. Because I've got 2 volts shared between 2 resistors. They get half each, 1 volt for this one, 1 volt for this one. So they must have identical resistances. Then we get rid of that one, switch it out for a 12 ohm resistor. So the easiest way to picture this now, for me, is like this. If I move that internal resistance so it looks like all the circuits I've ever done before in series, and I've got my internal resistance which is 4 ohms, my external resistance which is 12 ohms, and my model of my perfect EMF is 2 volts. No, wait, C. C. Is Tyler correct? Does anybody agree with Tyler? Nobody wants to talk. Okay, so if I've got 2 volts and it's split between here and here, then I've got 4 out of a total 16, which is a quarter. So I can times, actually I can do my potential divider here. So I've got 4 out of a total 16, so that gets 1/4 of 2, which is 0.5 volts. And this one here gets 12 out of a total of 16, which is 3/4 of 2, which is 1.5 volts, 1.50. They are a bit tricky, and it does say it's 1 mark, but all of these, as far as I can remember when I picked them out, said that they're 1 mark, but were worth 2 minutes, which is a bit tricky. If you've got any further problems, feel free to bring them along to Physics Workshop tomorrow in S349, 12:15 till 1:15. Be there or be there. Be there or be square, as George says, because you won't be around because you're a square. If you got 4.25, I don't know quite what you've done, but do feel free to bring your working in tomorrow. I'll bring the questions of my working, and I'll see you in class tomorrow, Harley, so we can do it then as well. It's been a pleasure. Thanks for watching. I'll see most of you tomorrow, I expect. Cheery bye. Oh, now I forget how to end the broadcast again. No problem, Jack. No problem, Harley. No problem, Carl and George and Tom, wherever Tom's gone. He's probably fallen asleep. It's too late for Tom. No worries, Will. Bye-bye.